this is our note. These are our notes on 9.3 logarithms. You guys, I think, have done logarithms in Algebra 2. I'm pretty sure you got to them. If not, we're going to talk about them here in Trig. What is a logarithm? A logarithm is an exponent. Actually, I should say the answer to a logarithm is an exponent. I'll show you what I mean. We write y equals log base b of x if and only if b to the y equals x. So I want you to notice that y is the exponent and it's the answer to the logarithm. B is the base, y is the exponent, and then x is whatever that base to the exponent is. So it's kind of crazy. This right here is, a lot of times we know the answer. What we don't know is what's the exponent. Okay. One of the things that we are going to be talking about, and we're just going to put this in our notes, is that there's something that's called a common log. And that is when a log without a base has a base of 10. So if you ever have a log and there's no base, they're like, wait, Miss Solozzi, there's nothing here. Well, that means 10 is the base. And when 10 is the base, a lot of times they don't write it in. I usually will go ahead with a common log and I'll fill in that 10. But as I told you, I'm a visual learner. I like to be able to see the base written. But whenever you have a log without a base, it has a base of 10. That's important for you to know. Okay? So let's just dive into some examples. Letter A, y equals log base 8 of 512. So the first thing I do is I rewrite my log exponentially. Every time I do a logarithm problem, I rewrite the log as an exponential equation. And then I solve my log. Okay. So I'm going to rewrite this as 8 to the y equals 512. So I've got to figure out how many times I need to multiply 8 by itself to get 512. So let's see. Let me do my work up here. I have 8 times 8 is 64 times 8. Let's see. What is 64 times 8? I get 8 times 4 is 32. 8 times 6 is 48, 49, 50, 51, 512. There you go. I had to multiply 8 by itself 3 times, so y equals 3. Let's go to part B. Notice there's no base, so I like to insert or write it with the base. So I'm going to put a base of 10 there. That's just how I like it. I know they don't have equals y the way they do here. You can write it any way you want. If you want to write equals x, equals y, equals whatever, I still rewrite the log as an exponential equation. 10 to the x equals 10 million. And I've got to figure out then what x would be. Well, when it's a base of 10, it's kind of easy. We can just count the zeros. 1, 2, 3, 4, 5, 6, 7, and it'll be x equals, why did I start to write 10? X equals 7. And that's because when I come up here, that would be 10 times itself 1, 2, 3, 4, 5, 6, 7 times, because you have 1, 2, 3, 4, 5, 6, 7 zeros. Let's go to letter C. I'm going to first write it exponentially. I'm going to just write equals x. So I have 3 to the x equals the 7th root of 3. I am going to, usually if something's written with a radical, we can change it to an exponent. If it's written as an exponent, a lot of times we have to change it to a radical. Usually we have to change whatever form it's in. So we're going to rewrite this. So we have 3 to the x equals 3 to the 1/7, because the 7th root, remember, we always have power over root. So get to the 1/7. Well, notice they have the same base. Therefore, x equals 1/7. Let's go on to letter D. Equals x. I'm going to rewrite it as an exponential equation. 8 to the x equals 1/64. Well, just like here, when I'm solving an equation, I need them to have the same base. So I'm going to rewrite this using the same base as this. So I'm going to rewrite this as 8 to the x equals 1/8 squared. Now, I haven't yet written it with the exact same base because this 8 is in the denominator. I need 8 to be in the numerator like it is here. So I'm going to say 8 to the x equals, if I cross the line and I bring the 8 up top, that exponent becomes negative. Now I have the same base, just like I have the same base here. And because they're both base 8, x must equal -2. Okay, let's go to letter E. Again, there's no base here, so I'm going to write in a 10 equals x. So I have 10 to the x equals 0. Well, the only way to get 0 is for 0 to be your multiplier. So we'd have to multiply 10 by 0. But we can't do that. We're multiplying 10 by itself. So there is no way to get 0 unless 0 is the base. So there is no solution for letter E. Because think about it. No matter how many times we multiply 10 by itself, it's going to get bigger. Even if we use a negative exponent, which would make it 1/10 times 1/10 times 1/10, it would get smaller and smaller and smaller and smaller, and it would get close to 0. Really close. I mean, think about it. Let me actually get a calculator and I'll show you. Okay, so if we have 10, obviously 10 to the first, 10 to the second, 10 to the third. It's getting bigger and bigger. If I do 10 to the negative first, 10 to the negative second, 10 to the negative third, it's getting smaller. It's getting close to 0, but it will never actually equal 0. That's why it is no solution. All right, let's go to letter F. Letter F, b to the x equals b. Technically, this has an exponent of 1. These have the same base, so x equals 1. Let's go to letter G. 4 to the x equals 8. Now, I know that if I multiply 4 by 4, I'm already at 16. It's already too big. So what I realize here is that I'm not going to be able to write these both with a base of 4 or a base of 8, so I need to change the base. So I'm going to rewrite 4 as 2 squared. And I'm going to rewrite 8 as 2 cubed. And remember, power to a power, you multiply. So we have 2 to the 2x equals 2 to the third. We now have the same base. Therefore, 2x must equal 3. So that looks like, divide both sides by 2, x is 3 halves. And that makes sense. We're going to take the square root of 4, and then we're going to cube it. The square root of 4 is 2, and when you cube 2, you get 8. So the 3 halves makes sense. We're going to take a root and a power. Let's go to letter H. Letter H, b to the x equals 1. I know that anything to the 0 power is 1. So x equals 0. Any base to the 0 power is 1. Gotta remember that. Alright, so who cares about logarithms? Who really cares? Like, why do we even study logarithms? One of the reasons, as we're going to see later in the unit, is to solve exponential equations. But why in real life do we study logarithms? It's because of the Richter scale. The Richter scale is used to measure the magnitude of earthquakes, and it's based upon the common logarithmic scale, which means base 10. So you've heard that, oh, that earthquake was a 2.5 on the Richter scale. And then you might hear that another earthquake was, oh, that one was a 3.2 on the Richter scale. And you might think, wow, they were really close. Not really, if we understand the Richter scale. So let's read this question here. How many times larger are the vibrations for an earthquake rated at a 4.5 as opposed to a 6.5? Well, remember that the Richter scale is a common logarithm, so it's a base 10. So 10 to the 4.5, and this is 10 to the 6.5. The 4.5 and the 6.5 are exponents. So we've got to figure out what do we have to multiply by to get to the 6.5. Well, remember, with exponents, when you have the same base, you add the exponents. So this becomes 4.5 plus x equals 10 to the 6.5. If you're confused how I got from here to here, let's do a little reminder down here. 10 cubed times 10 to the 4th is 10 to the 7th. Remember, you add the exponents because this is 10 times 10 times 10, and this is 10 times 10 times 10 times 10, which is 10 to the 7th. Okay? So that's why I added these exponents. Well, notice these have the same base. So 4.5 plus x equals 6.5. So x is 2. Therefore, it's 10 squared, or 100 times